us once again in the FinClear Cabin Fever webinar chat. Today, we're very lucky to have Michael Brett with us all the way from the USA. Michael is the Senior Vice President of Applications at Rigetti Computing, and he's leading the company's application development mission to connect customers and their use cases to Rigetti's quantum cloud service. An expert in complex systems, he has extensive experience developing and accelerating adoption of early stage technologies and delivering projects in aerospace, defense, and data analytics. The apps team at Rigetti focuses on analysis of challenging analytics problems for finance, insurance, and technology customers, applying expertise in quantitative analytics with quantum computing methodology. Michael has an Executive Master of Business in Complex Project Management and a Bachelor of Engineering in Aerospace Avionics, both from QUT. He was previously the Chief Executive Officer of QBranch, also a quantum computing firm, which was acquired by Rigetti last year. So thank you so much for joining us.
Great to be here. Good to see you again, Kristen.
Thank you. And likewise. So could you kick off and just give us a brief layperson's explanation of what a quantum computer actually is?
Sure. So a quantum computer is a new type of computer that uses a different kind of physics than what a computer that we're used to, a classical computer, uses. And so by starting right at the bottom, a different kind of physics, classical physics that we're used to, quantum physics is different. With a different kind of physics, we can build a different kind of computer that can do a different kind of math. And with a different kind of math, we can write a different kind of algorithm. And with a different kind of algorithm, then we can solve difficult problems that we can't solve on a classical computer. And so when we build a quantum computer, it's a totally different approach to how we traditionally put computers together. But in doing so, it gives us a bunch of new tools in the toolkit that we're able to use to solve tough problems. So I'm definitely not going to get into the weird, strange, bizarre world of quantum physics, but suffice to say that there are strange behaviors that go on in the world of the very, very small, it's sort of the subatomic scale. And it's those strange behaviors that we can use to build a different kind of computer and then solve a different kind of problem.
Okay. I mean, quantum computing is sort of not a new concept to a lot of us in that it has been floating around the atmosphere for quite a few years. Can you walk us through the history of it, where the idea started and where it's at today?
Yeah, so the idea was first postulated back in the mid-80s by the physicist Richard Feynman, who sort of put forward this idea, a thought experiment essentially, that said, you know, the world around us is a quantum mechanical world. If you've got a coffee cup in front of you full of hot coffee, there's a lot of quantum energy that's going on inside that, the heat and the way that, exactly go, the behavior of the coffee in that coffee cup is a quantum mechanical phenomenon that's happening. And our ability to simulate what's going on inside the quantum mechanical universe, whether it's hot coffee in a coffee cup or photosynthesis that's going on in leaves, or the way that molecules interact in drug discovery, our ability to simulate that behavior using a classical computer is limited, because you kind of got to match the quantum world of hot coffee in a coffee cup with the classical behavior of the binary behavior of a classical computer. And so Richard Feynman in the 80s said, if we want to get to the stage where we can simulate the quantum mechanical world around us, we will need a quantum mechanical computer to do that simulation, to match it together. And so that kicked off research. It was theoretical in the 80s and 90s, building up to some more experimental work in the late 90s and then through the 2000s. And it was really in the 2000s and 2010s that the first experimental devices of a quantum computer started to come together. So the experimentalists were able to take that theory and start to put together the first building blocks of a quantum computer. So that the fundamental units, things called a qubit or a quantum bit. Think of it like in a classical computer, we've got a bit, a switch, on or off, 1 or 0. In a quantum computer, a quantum bit is some probability of being 1 or 0 and an ability to manipulate that. So it was through the 2000s and 2010s that those first qubits were starting to be built and experimented on. And then really in the last 5 years or so, those qubits have been built into bigger and bigger systems. And so IBM and then Rigetti, not too long after that, launched the first quantum computers into the cloud in 2017. And it was just a 5-qubit device or a 9-qubit device, very small numbers of qubits, very limited power. But just over the past 3 years since then, we've seen a fairly rapid expansion of the capability of these systems. And so today in the cloud, Rigetti's got a 28-qubit device that we make available to our customers. Google did some pretty big breakthrough experimentation last year on a 52-qubit device. And so this is a really exciting time for this industry because what was a theoretical idea in the 80s, building up through to the mid 2010s, has crossed that threshold from being the domain of universities and research labs with scientists working on the bench and trying to get things to work, to now industrial R&D, where companies like Google, IBM, little old Rigetti, a few other startups like that, are starting to build more and more capable devices that we can do experimental R&D on.
Yeah, right. So where are they built? Where are the labs that they're built in? What do they look like?
The labs are generally within the research departments of large corporations like IBM, Google, Microsoft, or within startup companies like Rigetti. And this is a very complex endeavor. It's a very expensive thing to undertake. And so there's quite a lot of fancy looking equipment that sits around. But fundamentally, this is a really tough electrical engineering problem to build these together. And there's a couple of different ways to build the quantum computer. We won't dive into all of them, but in one particular fashion, you've got lots of lasers working together on a bench, manipulating atoms. And the approach that Rigetti takes, we use a thing called a superconducting qubit, which means we need to cool our systems to a very, very cold temperature. Operates at around 15 millikelvin, so about that much above absolute zero. And so our labs look pretty funky. There's some giant refrigerators that are in there that cool these systems down. But the kind of professions that we need to build these systems are electrical engineering, silicon fabrication, so building chips like Intel would, cryogenic engineering, mechanical engineering, software engineering, lots of theoretical and experimental physics and testing. So the cohort that comes together to build these systems is a very diverse group of professionals that are solving lots of difficult problems all at once, trying to get these systems to work.
Yeah, fascinating. And is it a big thing? Obviously, the quantum piece of it is a very small thing, but the kit that sits around it, how big is that? And are they portable? Or will they ever be?
I'm going to go out on a limb here. It's tough to make predictions, especially about the future and technology, but I don't think a quantum computer is ever going to be a portable device that you'll carry around in your pocket. This is a cloud-first technology. It's quite large systems. Ours are about the size of an elevator. So it's a human-sized sort of device. You can sort of stand around it and stand aside and get screwdrivers inside to fix things. And so this means that these machines are going to be deployed inside large data centers in a controlled environment. They're very expensive. They're quite powerful. They're a little bit temperamental, so they need some tender loving care to make them operate. So this is a cloud-first technology, and the way that users access these computers is the same way that you access Amazon Web Services today or other high-performance compute. Use your laptop, you do your coding, sitting on your lounge chair at home during coronavirus lockdown, and you send your problem off into the cloud, gets computed on a quantum computer, comes back, and you continue doing your work. And so that's how all of us at Rigetti are working right now, is just like everyone else in the world, working from home, but we're accessing our computers to solve problems.
So what kind of clients are accessing your computer, and what kind of problems are they working on? And how many people can access it at once?
So we can only solve one job at a time. So sequentially problems come in and we solve that problem and then give the answers back to the user. But the kind of customers that are looking at this are range from Fortune 500 level companies that are working with our machines to look at very challenging computational problems that they have in their business. So in the financial sector especially, things like portfolio optimization type problems, accelerating the training of machine learning algorithms. So how can they more rapidly do things like KYC and AML training of the machine learning algorithms. Some acceleration of Monte Carlo type problems. And I think the common element to all of those problems is that they are inherently probabilistic type problems. One of the key differences between a quantum computer and a classical computer is that quantum computers are good at some things. We can only do some particular problems. And one of the examples I like to give is that quantum computers are not that great at addition. And so if you asked a quantum computer, what's 2 + 3? The answer that you'd get back is, it's probably between 4 and 7, which is right. It's a correct answer. It is probably between 4 and 7, but it's not precise. So it's accurate, but not precise. And that's the trick with quantum computers, is we need to find the problems where getting a very accurate yet imprecise answer very quickly is useful to us. But if we need to worry about getting to the 20th decimal place and getting it exactly precise, then we're better off running that on a classical computer. So the challenge for us as the applications team inside Rigetti is working with our customers to find the kind of problems where solving it very quickly and getting a probabilistic answer would be sufficient to drive business value, rather than putting it onto a classical machine and using the time to solve a problem precisely.
So without giving away any state secrets, can you give us a use case that you've seen that either Rigetti has done or that you found interesting from the industry?
Yeah, so we actually just published some work recently with CBA in Australia, who we've worked with for quite some time. And this work was around a portfolio rebalancing problem. So how do you get from one portfolio construction to a different portfolio construction in the most efficient way possible? And so that's a series of trades that need to be made and need to be done in a certain order. And so we're able to show a very strong proof of concept there of getting from a portfolio construction in a more efficient way with a quantum computer. And I think we'll have another paper just like that coming out within the next week or so. So keep your eyes peeled for that.
I shall do. And if we can distribute that to our listeners today, I'm sure that the one that's published, I'm sure that would be very much of interest, because portfolio construction is very much of interest to our industry. Awesome. So what do you think is next? Obviously, quantum computing is on the bleeding edge already, but I guess you guys are already looking over the horizon to see what could be next. Can you put your futurist hat on for us again?
Yeah, so I think already today in the cloud, in a high performance computing environment in the cloud, whether it's on AWS or Google Cloud or Microsoft Azure, we already work in a mixed compute environment. We've got CPUs and GPUs from NVIDIA and TPUs from Google running alongside each other. And these are different pieces of hardware that solve problems in different ways. And part of the trick in high performance computing on the cloud is to allocate the right algorithms to the right hardware and get the most efficient pathway to a response. And so we've already got CPUs and GPUs and TPUs running alongside each other in the cloud, and quantum computers are just another tool in that toolkit. So a new type of computer that is complementary to those other systems. And this is my futurist part now, that's not going to be the last of them. I think there's going to be many more different kinds of exotic compute that get launched in a cloud-first environment. And we as application developers looking to solve problems in the most efficient way we can our job is going to be to make the most of all those different kinds of compute. So, quantum is great. It's going to be a breakthrough for some things, but even then, there's going to be other ways to solve problems that we're going to need different kinds of computers for. So we're going to be looking at for things like neuromorphic programming or biological type computers that will allow us to solve even more difficult problems in a different way. But it's that combination of all the different kinds of processes working together that's going to provide the edge.
Yeah, cool. So you mentioned CBA. That's pretty cool that they're at the forefront of all of this. Where is quantum computing at in Australia at the moment? Do we have one here?
So there are small ones in Australia. Australia has been one of the leading nations in the world in the science of quantum technologies. And I say quantum technologies to broaden it a little to not just computing, but also quantum communications, quantum sensing, quantum cryptography. There's a range of ways that you can apply the strange behavior of quantum physics to applications. And Australia has been, a world leader, genuinely a world leader in developing the basic and applied science of quantum technology generally. If you'd like to learn more about this, CSIRO on Friday releasing Australia's quantum roadmap. And so that will be the national agenda for quantum technologies that has been produced by CSIRO on not just their view, but it's kind of like it is intended to be the broad ecosystems view of government and industry and academia together to accelerate the development of the technology in Australia. So just in addition to that CSIRO work, we've also got two centers of excellence that develop quantum technologies, one led by University of New South Wales, one led by the University of Sydney, that are producing exceptional work. Microsoft has partnered very closely with the University of Sydney team and is adopting a lot of their technology into Microsoft's quantum computing effort. And similarly, the University of New South Wales has spun up a startup company called Silicon Quantum Computing that's been very well funded to commercialize some of their efforts. And so in Australia, we've got a huge body of knowledge and a huge capability in our people to continue to develop this, but it's not the kind of thing that Australia can do alone. This is a very complex technology, and we need to partner closely with allied countries like in the US, and I live in Washington, DC, to complement those programs that are happening here to make sure that we can get the most of that economic benefit.
Okay. We've just got a question here from Tony. Thanks, Tony. He's asking about the expense. They're very expensive, as you mentioned before. Do you think that's going to iron out in the future in the way that computers did?
It will, but they're expensive to build. But because we make them available through the cloud, it's offered as a by the hour kind of service. And so I think that's going to be the standard model for access to quantum computers. The price that we charge at Rigetti for time on our computers is $2,400 an hour to solve problems on our computer. And that's the same price whether you access our computers directly through Rigetti or whether it goes through our distributors with Amazon Web Services. Now, that seems like a high number, but if you compare that to the cost of running on a high performance computing system, a supercomputer, sort of the national supercomputer infrastructure at a university or a research lab, it's very price competitive with the kinds of problems that we can solve. So if you're solving a very difficult computational chemistry problem that might take an hour on a supercomputer at a research university versus a computational problem that the same problem that could be solved within minutes on a Rigetti quantum computer, all of a sudden that price differential looks very affordable on these machines. And so this comes back to my point earlier of we need to be able to make use of all sorts of different types of computers. So we put some tough problems on the expensive quantum computers and solve those quickly, and then some of the easier problems on the lower cost CPUs. But combining those together solves the problem for the application in a value creating kind of way.
Mm-hmm. Yeah, interesting. Something that I've always been wondering about quantum computing is what it will mean for security, particularly online. Can you talk to us a little bit about what sort of a greater uptake of quantum might mean for how we keep our data secure?
Yeah, so there's two parts to this answer. The first part is looking at one of the potential disaster scenarios of quantum computing, which is that there's a particular kind of algorithm that can only be solved on a quantum computer. And it's an algorithm called Shor's algorithm, S-H-O-R, invented by a mathematician named Peter Shor, based at MIT, who came up with this algorithm in the mid-90s. And this is an algorithm that can essentially crack some variants of modern encryption standards. So the kind of encryption that we use for internet security, for banking security, or the usual common kinds of encryption standards that are extremely challenging to break for a classical computer. But if we built a quantum computer that was sufficiently capable, I'll come back to that, then this algorithm could break those encryption protocols very, very quickly. Now, what does sufficiently capable quantum computer mean? It means that it's got a very large number of qubits at a very low error rate. And so the kinds of numbers that we're talking about are, so Rigetti, we've currently got a 28 qubit device. You would need about a 10,000 qubit device to solve this algorithm. So we've got some years away before this is going to be a threat. Maybe 10 years, maybe 20 years, but we're talking in that kind of region before companies like ours are able to produce machines that are capable of running this algorithm that could threaten encryption. So the bad news is, yes, it's a risk. The good news is we've got some time to address it. But then there's a twist on it. And the twist is that, let's say you are encrypting information today that's sensitive, and it's financial information, it's medical information, it's personal, private information in some way. And that information is getting moved around the internet. And that information got collected today and stored in an encrypted state with the expectation that a quantum computer would be available in about 20 years to read it. And so this is the imminent challenge that we have, is that even though our computers aren't capable today, the expectation is they will be in the future. And so we are all concerned about the sensitive information that we're passing around today, because it could be opened at a later date, and that could be just as sensitive. So in the US, the National Institute of Standards and Technology, NIST, is currently working through a process to come up with a set of recommendations for encryption standards that will be post-quantum cryptography, that'll be quantum computer resistant. And we're expecting to see the recommendations from this agency come out within the next year. And that will be a set of recommendations that will apply to government, to industry, to academia, to people that are worried about encryption. And we would advise folks to look at adopting those as soon as possible, with the expectation that it'll be some decades yet before a quantum computer is available of sufficient capability, but we need to address it now.
Oh, fascinating.
So, long answer to a short question.
No, that's a great answer, and it leads into another question that I had. And everyone who's watching, if you have a question, feel free to ask it via the Q&A button at the bottom of your screen. What does this mean for geopolitics and defence? I know that's an area that you have looked at before. This must be something that's being taken quite seriously at that level. What do you have comments to make on that?
Yeah, there's a couple of different drivers here. So this is a strategic national technology that's important to all sorts of countries. And it comes from two different kinds of pressures. One is the pressure for global supremacy in the artificial intelligence technology arena. So do we in the West anticipate maintaining an edge, an industrial edge, and a security edge over potential adversaries through the use of all sorts of kinds of artificial intelligence and machine learning type applications? And I think that that is, there's no controversy around the need to maintain that capability edge. And quantum computing is just one ingredient in that mix. So there are all sorts of different contributors to artificial intelligence. Quantum computing is clearly going to be one of the enablers that helps drive that. And so if we are to maintain an economic edge and a security edge in artificial intelligence, quantum computing needs to be part of that story. The second is around the understanding and use of encryption. So both the de-encryption technology, but also the encryption part of it, that nation states want to get access to quantum computing technology to give them a technology edge in that space. And so it's for those two reasons, AI and encryption, that governments around the world, the US, Australia, UK, Europe, China, Japan, Singapore, have all released national strategies for quantum technologies in the past 2 years and have identified this as a strategic national technology that they're looking to invest in quite heavily. Just to give you the numbers in the US, so just before Christmas last year, so 15 months ago, the US government signed the National Quantum Initiative, which is a piece of legislation that went through with 1.3 billion over the next 5 years to invest in quantum technologies. And so that money is starting to flow now through the various agencies. And we're seeing a lot of investment from the US government into quantum technologies generally to help advance the technology base there.
Awesome, great time for you guys to be in the field. That's excellent. I just want to take you back to the sort of first half of our discussion, and then we'll take a couple of questions. There's a couple here. You mentioned that quantum computers are great at solving complex problems in an imprecise way. This might take us down the rabbit hole a little bit, but I think we're willing to go there. What is it that makes them imprecise, and is that something that you're trying to solve for, or is that just how it works?
Quantum computers are inherently probabilistic devices. And the metaphor that I like to use here is that, let's say you flip a coin and the coin's spinning in the air. When it lands on the table, it gives a probabilistic outcome. It gives either a heads or a tails, a 1 or a 0 on there. When we operate a quantum computer, we are effectively flipping a coin in the air and manipulating the probability of that coin landing as heads or tails. Now, we can't exactly make it land heads or tails, but we can manipulate its probabilities, and we can have that coin affect all the other coins around it and give us a probabilistic answer. And so deep down in the physics of these devices, the strange behavior of quantum mechanics means that we're operating with probabilities as the building block of these machines. And so that means when we take it back up to the system level, we are getting a probabilistic response from these devices. So it's part of the inherent nature of these computers is that we're working with probabilities, and so therefore imprecise. And so we need to work with that as a feature rather than a bug of these systems. And so when we look at things like portfolio construction, we're not trying to get the precise answer to it. We're trying to find a very rapid probabilistic answer for what could be the optimal portfolio to go with. And then if we run that a couple of times, say 100 times, we'll get a probabilistic distribution and then can choose from that what the right portfolio might be. So we're very much working with the the inherent nature of these machines to generate probability distributions. That's the real outcome of how we work with quantum computers.
Awesome. We've got a question here from Alan, and he's asking whether a quantum computer would be able to work in its own capabilities such that it might develop itself, essentially, quite quickly. And he makes the point that the room that you're currently in wouldn't have fitted in the IBM 1620 he started in the 70s, which is now replicated on his laptop. So what do we say? Is Skynet going to become sentient?
Not anytime soon, that's for sure. But we are using some elements of quantum computing to help us improve the function of quantum computers. That's for sure. In much the same way that we use classical computers to improve the function of classical computers. Like we're incorporating design tools, and we're incorporating some of the machine learning type elements that we use for quantum computing to then inform how the quantum computer itself should be designed. And so there's that fun feedback loop of using the very tool that we've built to improve the tool. But it's not just a human in the loop. There's about 150 humans in the loop that are doing that work to improve it, and a lot of classical compute besides. So it's fun to do, but we've got a long way to go yet before it's sentient designing itself.
Alan says thanks, and just remember how. Look, that's fantastic. What was I had another question floating around in my head. That's right. So you were talking about other kinds of exotic computers, which sounds really cool. What are you seeing as someone who works at the forefront of computing coming down to sit beside quantum computers in exotic computing land?
Yeah, there's quite a bit. There's most of it is coming from the need to create specialist devices for specific problems. And to give you an example of this, there's a series of problems that are very difficult to solve in computational fluid dynamics. So if you're modeling oil passing through a pipeline, air flowing over the wing of an airplane, that computational fluid dynamics equations are very computationally intensive, and they're used in everything from designing automobiles to predicting the weather, and the set of equations there are very challenging for classical computers to solve. And a friend of mine is started a company to build chips that are specifically designed to that particular algorithm and only that algorithm. So like quantum computers can't do addition, his computers can't do addition either. But what they can do is solve computational fluid dynamics extremely efficiently. And so I think what we will see over the next decade or so is more and more specialist devices to solve problems like this. The computers that we all grew up with and have in our office, these are general purpose computers. They're good at doing addition, they're good at doing spreadsheets, they're good at playing computer games, they're good at doing all sorts of stuff, and that's why they sit on our desktop and we can do lots of things. But in high performance computing, for industrial computing, there's so many things that we need them to do one thing and do it really, really well. And so there's enough value in that one thing to go build a chip that's explicitly designed to do that one thing. And I think we'll be seeing more and more of that over the next decade.
Fantastic. Look, we're nearly out of time. We've got just a couple of minutes left, and we've got one question. I don't know who this is from. It's been asked anonymously, but I think it would be a great place to end. What complex problems does humanity face currently that quantum could possibly help us solve for a better future?
Yeah, we look for these all the time in our work because we want to help solve these kinds of problems. And the one that I like to think about is in the chemistry space. So going back to Richard Feynman's original hypothesis, how do we model the quantum mechanical world around us and better understand how that works, and the way that atoms interact with each other inside a molecule, which could allow us to do all sorts of wonderful things like design new kinds of drugs and to look at treatments and better understand the way that proteins fold and genomics and that kind of thing. But one of the things that I'm fascinated by is photosynthesis. We as a don't have a particularly good understanding of how photosynthesis actually works at the molecular level. It's a very complex quantum mechanical interaction. We've got light coming from the sun, something going on inside the leaf, sugar being created, energy being created, and oxygen coming out. And so what if we could understand that interaction almost perfectly, to the extent where we could synthesize photosynthesis as a civilization, and the ability to create energy from sunlight in such an efficient way, and to generate oxygen as a byproduct from that. Now that's very science fiction for what we do, but it's the kind of science fiction that I think we should be heading towards, because it ties back to that original hypothesis for quantum computing, and we will solve many, many problems along the way in order to get to that. So that's the best answer I got for that one.
That's brilliant. I love it. We shall be the green men. Look, I think that's it from everyone. So I'm just going to say thank you so much for joining us. It was a fascinating chat. It will be recorded, and the recording will be sent out this afternoon. So thank you so much, Michael. That was really, really great.
My pleasure, Kristen. Thanks so much. Thanks for coming, everyone.
Thank you.
Bye-bye.